Good afternoon, everyone. Let me see. Yep, I'm still Don Campbell, and I'm still very, very happy to be with you all. That means Susie didn't throw me overboard last night. Anyway, the lands around the Ring of Fire rise slowly out of the infinite Pacific, and some of us who've been on this ship for a while and those who were on it since Sydney know it seems like a pretty big body of water. Anyway, those lands tell the story of, well, probably history that's as old as the Earth itself. The ring is one of the most geologically significant areas in the world, and earth-changing forces are evident all around it. But first, it's kind of like an ad for something on television. But wait, first, here are the results of our kind of unscientific, or whatever you will, top 10 that we got from you, our guests, sites, man-made sites around the world. Actually, there were a total of 25 sites from all over the world that you named, and these are the top 10. The results were somewhat of a surprise. 9 sites that were chosen by you were on our list of 10, so I guess we came pretty close to being places you all have been. The top 2 vote getters here were tied, similar to what we had with the natural wonders, where we had 3 tied at the top. Here it was Abu Simbel in Europe and Christ the Redeemer in Brazil. I said it wrong?
Yeah, it's not Abu Simbel and it's not in Europe.
It's in Egypt.
That's right.
Yeah. All right, anyway, enough with the man-made stuff. Let's get started with our talk about the place that we call Earth. The Ring of Fire is where there are large numbers of earthquakes and volcanic eruptions, and they occur in the Pacific Ocean basin. Here there's a 25,000-mile long string of some 452 volcanoes, and over 3/4 of all of the active volcanoes in the world are located on the Ring of Fire. About 80% of the largest earthquakes occur around the ring, and it's the most seismically and volcanically active zone in the world. Now, to better understand it, we need to go back a little bit in history. Now, I'm not going to take you back 4.5 billion years. I'm only going to go back maybe 4 billion. No, we're going to talk a little bit about the early history, about how the Earth was formed, and the formation of the continents was first suggested way back in 1596 by a Dutch map maker by the name of Abraham Ortelius. He said that the Americas were torn away from Europe and Africa by earthquakes and floods. He went on to say that the coastlines of the continents matched as if pieces of a jigsaw puzzle. In 1858, a geographer by the name of Antonio Snyder Pellegrini actually drew the 2 maps that I just showed, the first one and this one, and that was his concept of how the American and African continents once fit together and then separated. It is kind of an amazing fit. It wasn't until the 20th century that it was seriously considered a scientific theory. A lot of people thought, oh, it's just hogwash. In 1915, a German meteorologist, whose name was Alfred Wegener, speculated that there was once a supercontinent, and he coined the term from the Greek words for entire and earth, and he called it Pangaea. So the whole earth, single continent. Wegener estimated that that was about 200 million years ago, and that supercontinent subsequently broke up into smaller pieces. He based his theory on a remarkable fit of the African and the South American coastlines. Of course, he read Snyder Pellegrini and Ortelius's works, and he used his own studies as well. Now remember, this guy was just a weatherman. You know, he did the 6 o'clock weather on Channel 6 for a lot of years. Anyway, he believed that Pangaea's breakup and the movement of the continents were caused by what he termed as continental drift. And he said it was the only way to account for the wide ranges of climate seen in the fossil records on each of those continents. He saw similarities in the rock structure, plants and animals, fossils found on South America and Africa. So he saw these similarities vastly separated. He reasoned that it was impossible for organisms and rocks to move across the oceans. Obviously, he had never seen a rock that could swim. There are rocks that float, but not that well. Anyway, Wegener's concept was a major contribution to science. He linked very unrelated and dissimilar facts to put his whole theory together, and he used the disciplines of anthropology to seismology and even to zoology to fit it all together. Wegener raised many, many questions. Among them were, why are there coal deposits in Antarctica when coal is created by decaying plant life that grows only in tropical jungles? Why are remnants of glaciers found in equatorial Africa and India? This guy was attacked from the very beginning, and continental drift wasn't accepted during his lifetime. Remember, he was a meteorologist, and he was stepping over into the territory of geologists. It wasn't until after his death that the theory was finally verified. In the mid-20th century, scientists actually found a dinosaur in southern Australia that had originally lived in Antarctica. They called it a polar dinosaur. Hey, why not? It came from near the South Pole. Actually, it had adapted to very cold temperatures, it had warm blood, and also had night vision. It foraged for food in the winter and became extinct just recently, 65 million years ago. In 1991, paleontologists found another dinosaur. This one was in Antarctica, only about 300 miles from the South Pole. But this one was different because they believed that it had lived in the equatorial, up in the middle of the Earth, where it's very hot in climate, so near the equator. How did it get there? Well, the whole Earth kind of moved around. That's how it got there. Continental drift can better be explained if you take a look at this thing of the Earth. It's what makes up the Earth. And science defines the Earth as having a crust, a mantle, and a core. Now, the crust, or the outermost layer, which is just kind of the thin skin around the outside, is very rigid and quite thin. It's brittle, and it can rupture. Crust under the ocean generally is about 3 miles thick, so it's not very thick under the ocean. Under the continents, maybe 7 times that, 20 miles, 21 miles thick, except under some of the mountain ranges, it could be as much as 60 miles thick. But still, when you think about how big the Earth is, that's a pretty thin crust. Now, beneath the crust is the mantle, and that's a dense, hot, semi-solid layer of rock and heat. It's about 1,800 miles thick. And in this layer, both temperature and density and pressure increase with depth. Of course, I guess that would be natural. Anyway, the upper layer, the mantle core, is cooler, and as you get further down, it's hotter. The upper is a little more rigid, the lower a little more liquid. At the center of the Earth is the core, and that's the little round ball in the middle. And actually, the core is made of 2 parts. There's a liquid outer core, and then there's a solid inner core. And the inner core is mostly iron with a little nickel thrown in, and again, it's very, very hot. Floating around on the mantle are very large pieces of the Earth's crust that are called plates. They're not quite like the plates we have up in the terrace. They're a little different than that. They're very big. The red arrows that are on this slide actually show the direction those plates are moving in relationship to each other. And it's very dynamic. All of them are moving around a little bit. They're not moving super, super fast. I'm going to show you how fast they move in just a minute. And the stars on this particular slide indicate where there have been some relatively recent major earthquakes. There are 12 major and several smaller plates all around the world. The plates developed very early, maybe as early as 4.6 billion years ago when the Earth was first forming. And they've been kind of slowly drifting around ever since. The outlined area there that just bounced in with a big earthquake is where the ring of fire is in relationship to all of those plates. It's composed mostly of Pacific plate rubbing against other plates. The movement of those plates is called plate tectonics. It comes from the Greek root word to build. Where one plate meets another, there are flaws in the Earth's crust. The flaws are generally called faults, and that's where most earthquake centers are, and also there's quite a few volcanoes that happen. And one great example that some of us are quite familiar with is the San Andreas Fault that cuts through 2/3 of the state of California. And here the Pacific plate has been slowly grinding past the North American plate and sliding a little bit under it. And that's been going on for about 10 million years at a rate of about 2 inches a year. Your fingernails grow faster than that. Sometimes all of that activity gets stuck. We'll talk about that in just a second. Plate research has led scientists to study underwater because there's a lot of new information that they can gain there. And this is a computer graphic of depth measurements that were taken in mid-ocean in the Atlantic. About 2/3 of the Earth's surface lies beneath the water. Before 1800, all of the oceanographers, the geographers, everybody, the geologists believed that the bottom of the ocean was just as flat as that dance floor. It wasn't until very late on, at about 1855, that a chart published by a guy named Matthew Morey revealed that there were mountains in mid-ocean. The underwater mountain ranges average probably 15,000 feet high from their base. To give you an idea how high that is, that's nearly taller than all of the mountains in North America. The ridge was confirmed when they were laying the transatlantic telephone cables. Scientists believe that the ridges along the crest of the undersea area are weak zones where the ocean floor is actually being split apart. It's actually making the oceans a little wider. New magma or molten rock from the deep zones in the earth rise and create new oceanic crust. This action over millions of years is responsible for those mid-ocean ridges. The idea became called within a geological community ocean or seafloor spreading. It's evidence that the rifting that tore the original Pangaea apart, you can go see it. Actually, if you want to go put your feet on it, you can go to Iceland and you can put 1 foot in Europe and 1 foot in North America, and if you wait long enough, your feet will move farther apart. Of course, it might be several years before your feet move very far. Anyway, advances in seismology have provided proof that earthquakes and volcanic activity occurs even along those deep ocean trenches and submarine mountain ranges. This is a video clip from the University of Delaware. It's a phenomenon known as a deep ocean vent or a black smoker, and those are often found near the trenches or the ridges even, where the seafloor is spreading. Deep sea hot springs contain very dark colored minerals that come up as sulfides, and that sulfides are of iron, copper, zinc, nickel, and a whole bunch of other metals. Surprisingly, way down there where there is no natural light, there are vast colonies of life. All kinds of little critters and other things live down there. Mapping the Pacific Ocean floor revealed that trenches there were thousands of miles long, and some of them were 8 or more miles deep. Many are along the plates on the western edge of the Ring of Fire, and those particular trenches are caused by subduction. Well, this kind of tells you what subduction is. Subduction is where one plate actually is compressed or sliding down under another plate. And you can see it in this particular slide where you've got an ocean with a kind of a ridge in the middle that's making new oceanic plate, and it's pushing the ocean apart further and further. And when you get to the either side, you can see it subducting. That plate is subducting down under the other two plates, and along where that seam is, there's trenches on both sides. Those opposing actions are the thing that keeps the Earth from getting bigger or even from shrinking. Now, the Himalaya Mountains are a very good example of the whole idea of plate tectonics and this is caused strictly by plate movement. A lot of people thought for many, many years that the Himalayas were all caused by volcanoes. That's not really what happened. What happened was the Indian plate was way down in the southern hemisphere. It was attached to Africa, South Africa actually, and it broke free as the whole thing started to come unwound, and it started moving north. And it was moving along pretty fast. In geologic terms, it was moving at lightning speed, 7 inches a year. That doesn't sound like too much to us, right? But think about something that's millions of times bigger than this ship moving at that speed. That would be pretty impressive. Anyway, it finally collided with the Asian plate. And when it did, it, instead of subducting under or sliding past, it just bumped up against it. And when it bumped up against it, it was like pushing the outer ends of a throw rug together. What happens? The middle buckles up. Up came the Himalaya Mountains, and the Tibetan Plateau. Anyway, the collision of those plates caused Asia to bulge outward to the east. Basically, what's to the east? Japan and Southeast Asia. That's what's to the east. And it was bulging out toward the Pacific. The result was a buildup of some tremendous stresses within the Earth's crust. And those stresses are only, even today, only relieved by earthquakes. The earthquake that happened while we were on this cruise, actually, in Nepal, was strong enough, to give you an idea, to move that little mountain about 2.5 inches, all by itself. That's a lot of pressure and a lot of force. Okay, earthquakes are movements of the Earth's crust when the energy is released. Now, it can be a pretty sudden jolt. I mean, some of us have experienced what I would classify as a pretty severe jolt from an earthquake, and others don't really have the experience of enjoying that. Anyway, that also can happen in a very slow process that's called creep. Fault creep movement is generally non-threatening. I mean, you don't get hurt in a creep. A creep might hurt you, but no. An earth creep is just where the earth just kind of shuttles along, and it might be millimeters a year. It's very slow, very gentle, and the only thing it causes problems for is fences and sidewalks and roads and that kind of infrastructure stuff, because if they lie across the place it's creeping, it gets bent. So it's a maintenance problem. It's a nuisance in that respect. And along some faults, there's almost constant movement and very low levels of vibration. Some places, if you put a microphone on a hard surface, you can actually hear the earth vibrating in the creep. Now, seismographs are instruments that measure the magnitude of an earthquake or the creep itself. And they use a standard scale, and the amplitude of the waves is recorded, and that's assigned a value. Now, today, that gauge, which is formerly called the Richter scale, is simply referred to as the earthquake magnitude scale. So each increase of number of 1 is an increase of 10 times. So a magnitude 1 earthquake is 1. A magnitude 2 earthquake is 10. A magnitude 3 earthquake is 100, and so on until you get to magnitude 9, and that is a really big earthquake. That's 900 times as big as the 1. Let's visit some of the places that have been impacted by earthquakes, tsunamis, and volcanoes. They're all situated on a ring of fire. California is composed of mostly continental crust. Its low density keeps it from riding up above the oceanic crust, so the oceanic crust is pushing down a little bit and it's pushing north. The Great San Francisco earthquake in 1906 ruptured along a previously locked segment of the San Andreas Fault. It had a magnitude of 8.3 on the Richter scale. That's 830 times bigger than the smallest that you could record. The shaking was felt for a long time. It lasted for several minutes, and the city of San Francisco was devastated. Movement was felt from Oregon to Los Angeles and inland as far as central Nevada. The fault was ruptured both north and south for about 296 miles. Along the break, the ground shifted by up to about 25 feet. North of San Francisco at Point Reyes, actually you can go see this at the National Seashore up there, there is a milk shed that was attached to a barn, and during the earthquake it moved to the other end of the barn. I bet the cows were thrilled with that one. Anyway, the earthquake and the resulting fire are remembered as one of the worst natural disasters in the history of the United States. 1964 earthquake in Anchorage, Alaska, lasted for about 5 minutes. Now, to give yourselves an idea how long 5 minutes is, just stand, even just with the little motion we have on a ship, stand someplace unsupported, close your eyes, have somebody else keep the time for you and tell you when 5 minutes is up. I guarantee you it will seem like an eternity. And if it's an earthquake, it does seem like an eternity. Anyway, that one had a magnitude of 9.2. It was the most powerful earthquake in North American history and the second most powerful ever recorded on Earth. The strongest was, just so you know, it was in Chile in 1960, and that one was at 9.8. Ground movement changed the landscape. In Alaska, east of Anchorage, the land dropped by 8 feet. Some areas of Kodiak, 200 miles away, were raised by about 30 feet. The resultant tsunamis caused damage in Hawaii, Japan, British Columbia, Oregon, and California. The stresses that accumulate along a locked area of a fault and its sudden release can be visualized, and you could do this at home. This one you can do, and your spouse or your kids won't think well, they might think you're a little weird. Go get yourselves a green stick, pretty good size one, and start to bend it. And it'll bend, and it'll bend, and it'll bend. At some point in time, that stick will break. And if you think about it as it breaks, you're going to feel a little bit of a vibration in that stick. And that's the exact same thing that happens with an earthquake. When the earth finally breaks, it shakes. That's the earthquake. And you can do that, and you won't get anything damaged, I hope. A 9.0 magnitude undersea megathrust earthquake occurred just lately in 2011 in the Western Pacific. Initially, they recorded it as a 7.9, but the magnitude was upgraded to 9.0. The epicenter was 45 miles east of Oshika Peninsula in Japan, and the nearest major city to the quake was Sendai on the island of Honshu. Shaking there lasted for 6 minutes. There's another one for you to try with your eyes closed. The major quake was preceded by quite a few foreshocks, and then hundreds of aftershocks followed it. 1 minute before the earthquake was felt in Tokyo, a Japanese earthquake early warning system sounded an alarm, and that told the people there was going to be some heavy shaking. And everybody now believes that it was that warning that may have saved many lives in Tokyo and the surrounding area. It made portions of Japan wider than before. The Pacific Plate, that whole great big thing that was surrounded by that red, may have moved westward between 66 and 130 feet. The quake moved portions of northeastern Japan as much as 8 feet closer to North America. Pretty big movement. Shifted the Earth's axis. You know, this big bubble that we're on, it has an axis going through it, and the Earth spins around it. Well, that axis moved by 10 inches, and the Earth's rotation slowed. Changed that rotation, shortened the day by 0.002 of a second. It doesn't sound like much, but think about how big that mass is and how much that change had to be. The 2011 Japanese earthquake resulted in a major tsunami, caused massive destruction along the coast, and devastated entire towns. Thousands of lives were lost. A wave that was 128 feet high was estimated to have hit parts of the Japanese coast. A 250-mile stretch of the coastline had dropped by 2 feet, and that allowed the tsunami to travel much farther inland than it would have normally gone. The Japanese Coast Guard said that the quake shifted the seabed 79 feet and elevated some parts of it off the coast by up to 10 feet. That tsunami spread across the ocean, and destruction occurred in low-lying areas such as coastal India, Thailand, Sri Lanka, going to the west. In most countries bordering the Pacific, it caused relatively minor damage. Chile's Pacific coast is one of the farthest from Japan. It's 11,000 miles away, but it was struck by tsunami waves that were 7 feet high. What caused all that destruction? Well, this is a little demonstration. The Earth had occurred where the Pacific Plate is subducting underneath the plate that's alongside of Honshu. The Pacific Plate moves at a rate of 3.1 to 3.5 inches a year. Again, not really super fast, but geologically pretty fast. And it dips under Honshu's plate, and it starts to build up tremendous amounts of energy when it gets stuck. The motion is then pulls the plate further and further down until finally the stresses allow it to pop back up. And that rupture was about 300 miles long. Because the boundary and the subduction zone in the area of the rupture were really not very straight. It's a very wiggle-waggly kind of a line. The magnitude of the earthquake was a surprise to a lot of seismologists. Earthquakes and underwater landslides and eruptions of volcanoes under the water occur in oceanic areas, and they often trigger tsunamis. Normal wind-driven waves generally stay pretty much within the boundaries of the sea, and the waves don't normally come up onto the shore very far. During a seismic event, the seafloor may shift many feet, and an enormous amount of water starts to move. That results in a series of waves that race across the ocean, and the speed of those waves moving across the ocean could be 500 miles an hour. The word tsunami means harbor wave, and they really pose a very big danger to coastal communities. A lot of people call them tidal waves, but they don't have anything to do with the tides. They strictly are a seismic event. As a tsunami approaches the shallow water near the shore, the water will actually recede back as that thing is speeding forward. And that whole mass of water will then rush in, and it'll come in with great speed and height. Now, to us out here in deep water, if there was a tsunami going across the Pacific right now, we just felt it. You wouldn't even realize you went over it because it'll just be a little bump in the ocean. Of course, that little bump in the ocean is moving a tremendous amount of energy at 500 miles an hour someplace else. This is a computer animation of the tsunami that followed the devastating earthquakes in Indonesia several years ago. The red and yellow colors that you can see here show the intensity and the wave heights as they flowed out from the epicenter, and it cycles a couple of times so that you can see it. The International Tsunami Information Center was created back in 1965, and it was established to monitor the Pacific Ring of Fire because that's where all of the interest was at the time. But they've now expanded it out to include the Indian Ocean. It issues warnings that are based on an earthquake strength and wave heights that are gathered from sensors out in the ocean. And since the Indonesian quake, we've now been able to see tsunamis and measure them all over the world. This is a graphic, just a quick static graphic of the tsunami that was generated in the 2010 earthquake in Chile. The numerical scale is the time estimated in hours out to 20-some hours over when you get near Japan and Vladivostok. The colors represent the height of the waves as it goes out from that particular earthquake. And remember, that earthquake was largely on shore, so it wasn't so much as a seaborne event like the one in Japan. Now we finished with the shake and our little cooking demonstration here, so let's talk about the bake. She got it. Anyway, plate movement around the Pacific is also responsible for volcanic activity that really gives the Ring of Fire its name. Some of it's not really very spectacular. In 1943, there was a little fissure that opened up in a cornfield in Paracutin, Mexico. The earth shook and it bulged, and the farmer's out there wondering what's coming up in his fields. There was fine ash and dust and some gray smoke and kind of the heavy smell of sulfur that was coming up out of his field. The ground hissed and it smelled pretty bad, and I guess he moved his cows out of the way. Anyway, by the next morning, there was a cone that was about 30 feet high. Well, I mean, what are you going to do when you got something coming up out of the ground that's like that? It grew another 120 feet during that day. The eruption continued for 9 years, and it ended when the mountain was finally about 1,500 feet high, and the poor farmer's fields were all gone. But it never did spew any lava, rock, or anything like that, just dust and smoke and ash. Volcanoes such as Mount Helens in Washington State in the U.S. erupt with a very explosive force, and their magma is very stiff and thick, and it doesn't allow gases to escape, so it generates pretty tremendous pressures inside of the mountain. And finally, those pressures will fracture the rock surface until it suddenly just bursts out in a very violent eruption. Now, here's one you